Hi, this is on process annealing. So we are going to look at process annealing. So it is usually employed when using. It's usually used when percentage of carbon is less than 3%. Okay, so we only use when the carbon is less than 3%. So as you can see down here, this is the phase diagram that we had. So we are looking at process annealing down here now. Okay, so we're going to look at process annealing, and the thing is you can do it at higher, okay, higher than 0.3 you can. So however, it is time consuming when percentage of carbon is greater than 0.3%. Okay, this is because you need to heat up at a higher temperature when it's greater than 0.3%. So why we need to carry out process annealing is to recrystallize the material after it has been cold work. Okay, so we only carry it out when we have to recrystallize the material after it has been cold work. So the term that's new down here for all of you is what do we mean by cold work. Okay, the term that's new is what do we mean by cold work. Okay, so cold work basically, cold work is to induce plastic deformation at room temperature. Okay, so you deform the material at room temperature. That's what we call cold work at room temperature. Okay, so a critical thing to remember is a critical thing to remember for us all is that there will be no change in percentage of perlite and ferrite. Okay, so important critical component over here is there will be no change of percentage of perlite and ferrite. So that is why, okay, it's below the 723 line. Okay, you don't need to go from perlite transform to austenite. Okay, and in process annealing, which is always true, okay, in process annealing, the higher temperature that you use, the longer the time you need to cool. Okay, so in process annealing, this is what has been since written down here, that when higher temperature is used, okay, the time required for recrystallization to occur is shorter. However, there will be higher tendency for geometric distortion to occur. So that's why over here, what you see, the range of temperature, right? The range of temperature is so wide. Okay, look at the range of temperature, right? Temperature is so wide over here when we do process annealing. So when do we carry out the next thing you ask? We're gonna ask is when. Okay, when do we carry out process annealing? So what is it actually used for? Okay, so I'm going to give a example. So in this example, what you see is that the steel Okay, that a steel will fracture after 20% of elongation. Okay, so we see a steel over here. Okay, so this is example. We know in general steel, let me finish copying first. Okay, in general steel will fracture at about 20%. So if this is our initial geometry of 1 meter, and we want our final geometry to be 1.5 meters, so what we have is a plastic strain of 50%. So if we stretch 50% at one go, okay, if we deform, okay, we deform or plastically deform, okay, we plastically deform the material without process annealing, okay, the material will fracture, unfortunately, because the strain required is equal to 50%. Unfortunately, the strain at fracture is equal to 20 or 0.5, and the strain to fracture is 0.2, and we realize that the strain required is greater than strain of fracture, so that's why process annealing is required. If not, the structure will fracture, yeah? Right? If not, the structure will fracture. Right? So now, let's incorporate process annealing. Okay, we're going to incorporate. So what does process annealing do? So we incorporate process annealing. So what it does is the first, so there are stages, okay, there are stages. So I'm going to do this first. So it's going to be in stages. So in stage 1, okay, we're going to induce a plastic strain of 0.15. Okay, so 0.15 we know over here is less than the epsilon fracture, which is good news. You don't need to break. Okay, then you calculate the final length after stage 1. So this is the unstressed. This is the initial one. Okay, so this is let me use the next page. Sorry. So this is the initial material. Okay, so this is the initial material. Alright, so this is initially unstressed. Right, so this is the unstressed. So what we're going to do is we're going to stretch it by 0.15. Okay, we're going to stretch the whole thing by 0.15. Strain. So when that happens, when you stretch it, what happened to the, you can see what happened to the microstructure down here. So all this over here, so initially they are what? Round. Right? So now all this microstructure are distorted due to plastic deformation to oval shape. Yeah, as you can see from here. Right? Then stage 2, once from here, stage 2, right? So at stage 2, we are going to go through process annealing. So what process annealing does, okay, what process annealing does is it erase the plastic strain, okay, and the stress also, because when process annealing you have no stress, right? So what you see over here, okay, what we see over here is after process annealing, your microstructure become round again, right? It recrystallized to become round. Percentage of perla and ferrite did not change, and this is after process annealing. And then stage 3. So what you do at stage 3 now is you go through another. You're going to induce a plastic strain of 0.15 again. Okay, you're going to do it again. So you're going to induce a plus. So you calculate the strain you're going to induce. Okay, the formula is very straightforward. Right, so what we have is the length after stage 1, which is 1.15, and then you calculate change of length, and after stage 3, okay, after stage 3 it will become 1.325. So what you do next is you send it back. So from here you send it back to stage 2. You repeat stage 2 again for process annealing. Okay, you repeat it again, and then finally what you will get, okay, if you look at the history of the process, right? So now we're going to look at the history of the process. So I'm going to draw stress strain graph, right? So what we have down here, so we have stage 1, right? So we heat up stage 1, it goes up here, then we carry out process annealing, we bring it back to 0, right? Then we go to stage 3, we plastically deform again at room temperature, then we cool it down again, okay. Then after that we heat it up again, stage 5, sorry, we plastically deform again, bring it down, it raises to 0. Now we know this range over here, every stage over here is only 0.15, 0.15, 0.15, and finally somewhere around here, sorry, is the graph is, maybe you have to do a bit more, 0.15 strain. So you never hit fracture at all, okay. So again you stretch, okay, and then after you stretch you bring it down due to process annealing, okay. So this is how process annealing is used. As mentioned earlier, it should not be used where percentage of carbon is not greater than 0.3%, because it takes longer time to do recrystallization. Okay, so that is all. I'm going to stop here for process annealing. Thank you.